This is the last part of section 5.3, and we want to talk about theorems telling us when a matrix is diagonalizable. So let's look at, I put theorems 5, 6, and 7 into one box for you in your textbook. The first theorem we talked about last time, and that's the big theorem that says A is diagonalizable if and only if A has n linearly independent eigenvectors. The second theorem says A is diagonalizable, sorry about that, if and only if that geometric multiplicity is equal to the algebraic multiplicity for each eigenvalue. Now here's a reminder of what geometric and algebraic multiplicities are, but I can show you that theorem with a couple of examples. The first example we did, this matrix here, the algebraic multiplicity of lambda equals 4 was 2, but the geometric was 1. Since the geometric wasn't equal to the algebraic, we found that A was not diagonalizable. Okay, A is not diagonalizable. Whereas here in the second example we did, we found the the algebraic multiplicity, the AM of lambda equals 2 is 2. And then when we found a basis for the eigenspace, we found two vectors. So the geometric multiplicity for lambda equals 2 is 2 also. So the algebraic was equal to the geometric. And then for lambda equals 1, the algebraic multiplicity was 1. Lambda equals 1, algebraic multiplicity is 1. The geometric multiplicity is always going to be at least 1, because you're always going to get at least one eigenvector, and it turns out that the geometric multiplicity is 1 also. So in this case, for each eigenvalue, the geometric was equal to the algebraic multiplicity. All right, and that's what that theorem says. And then lastly, theorem C, if A has n distinct eigenvalues, A is diagonalizable. Now, that is a one-way theorem. It does not say if A is diagonalizable, it has to have n distinct eigenvalues. But if you have n distinct eigenvalues, then A is diagonalizable. And here's an example of that. Here we have a lower triangular matrix. Lower triangular. So the eigenvalues are on the mean diagonal. Eigenvalues are 2, 6, and 1. So we have a 3 by 3 matrix with 3 distinct eigenvalues. So by part C, A is diagonalizable. And the reason for that is when we go ahead and find a basis for the eigenspace for lambda equals 2, 6, and 1, we're going to get one vector for this guy, one vector for that guy, and one vector for this guy. And we'll see that we have 3 linearly independent eigenvectors. So we would be able to diagonalize. And the matrix D would be 2, 0, 0, 0, 6, 0, 0, 0, 1. And then the matrix P would be, I don't know, whatever the eigenvector corresponding to the value 2 is. So I call that P1. Put that in as my first column, and then P2, and then P3. I'd have to go actually find those vectors, which I'm not going to do. I just want to illustrate, if you have a 3 by 3 matrix, 3 distinct eigenvalues, you can automatically say A is diagonalizable. All right, suppose we want to diagonalize a 4 by 4, and the characteristic polynomial is this. What eigenspace are you going to find first? Well, you would be wasting your time to find a basis for the eigenspace for this guy or this guy first, because you know you'll get at least dimension 1 for each of those. But then if you went to try and find a basis for the eigenspace corresponding to lambda equals 2, if it didn't have geometric multiplicity be 2, you wouldn't be able to diagonalize, and you would have done all this work for nothing. So I would do lambda equals 2 first, since if the geometric multiplicity is less than 2, you could stop and say A is not diagonalizable. All right? If the geometric multiplicity were equal to 2, then you'd have to go ahead and finish the problem. But in the case that the geometric multiplicity is only 1, since the geometric would be less than the algebraic, you wouldn't have to finish the problem. Here's a couple more like that. Suppose A is 3 by 3 and has 2 eigenvalues. If each eigenspace is one-dimensional, is A diagonalizable? Yes, no, can't tell. Well, we've got lambda 1 and lambda 2, 2 eigenvalues. This guy's one-dimensional, and this guy's one-dimensional. That's 2. In order for A to be diagonalizable, you need 3 linearly independent eigenvectors, because A is 3 by 3. So the answer is no. You would need 3 linearly independent eigenvectors, and you only have 2. All right, suppose A is 7 by 7 and has 4 eigenvalues. So lambda 1, lambda 2, lambda 3, lambda 4. One eigenspace is 2-dimensional. Let's say lambda 1 is 2-dimensional. And one of them is 3-dimensional. Let's say lambda 2, 3-dimensional. So we've got 2 vectors there and 3 vectors for lambda 2. We know we'll have at least 1 vector for lambda 3, because that would be a minimum of 1-dimensional. Same with lambda 4, minimum of 1. So we'd have 3, 4, 5, 6, 7. So yes, 7 linearly independent eigenvectors. So you could say yes. Okay. The next ones are just solved for you. I've already did them, but I just want to illustrate some things here. If you left multiply a matrix by a diagonal matrix, you scale the rows of A by the entries of D. Whereas if you, as we saw in the beginning, if you right multiply by a diagonal, that scales the columns. So that's just a quick way to do that multiplication without having to think too much. The next 2 examples are here just so that you see that the conditions of diagonalizability and invertibility are completely independent. There are matrices that are invertible and not diagonalizable. Here's one. And there are matrices that are diagonalizable but not invertible. Here's one. So the 2 conditions are completely independent. All right, true false time. So you might want to pause it, see if you can do these, and then come back, and I'll do them with you. All right, we're back. A is diagonalizable if A is PDP inverse for some D and some invertible P. False, what's missing is the word diagonal D. So just because you call I'll call a matrix D, it doesn't mean it's diagonal, you have to say it's diagonal. So for some diagonal matrix, diagonal would go there. For some diagonal matrix D and some invertible matrix P. B, if Rn has a basis of eigenvectors of A, then A is diagonalizable. That's true because a basis of eigenvectors would mean that you had n linearly independent eigenvectors. Because a basis has to be linearly independent, but if you have an n by n matrix and you have n linearly independent eigenvectors, then that matrix is diagonalizable. Okay, A is diagonalizable if and only if it has n eigenvalues counting multiplicities. That's false. A matrix will always have n eigenvalues if you count the multiplicities. It's diagonalizable if and only if it has n linearly independent eigenvectors. Okay, D, if A is diagonalizable, it's invertible. False. C5 above. So example 5 right above this section. And then this one's false too. C number 4 above. All right, now I guess we're going back to A for some reason. A is diagonalizable if A has n eigenvectors. Well, that's false. They have to be linearly independent eigenvectors. B, if A is diagonalizable, then it has n distinct eigenvalues. False. See the example, page 2. So here we had only 2 distinct eigenvalues, 2 and 1, but A was diagonalizable. All right, and the last one. This one's not obvious, but it is true, and I'll explain why. This is true. If AP is PD and D is diagonal, then the non-zero columns of P must be eigenvectors of A. This is actually part of the proof that you can read at home of the diagonalization theorem, but let me just do a quick explanation. The matrix AP is the way we multiply two matrices by definition, not in practice. In practice, we do dotting of rows and columns, but by definition, AP is the matrix AP1, AP2, APN, where I'm calling P1 through Pn the columns of P. So P is P1 through Pn. Those are the columns. And then conversely on this side, PD, so this is AP, and PD is the matrix P, which is P1, it has columns P1 through Pn, but then we're right multiplying by a diagonal matrix D, and we know that that will scale the columns of the first matrix. So this is going to be lambda 1 P1 through lambda n Pn, where I'm calling the lambdas are the diagonal entries of D. And then if you set each column of the first AP equal to each column of PD, AP1 is lambda 1 P1. Since P1, the non-zero columns of P, we're assuming okay, so in order for you to be an eigenvector, you have to be a non-zero vector. So if your P1 is non-zero, then this equation here would say that P1 is an eigenvector for A, corresponding to eigenvalue lambda 1. So again, that one's not exactly obvious, but it is in your true false in your homework, so I did want to talk about it. That's going to finish off this chapter. We're only doing 3 sections of chapter 5, but we will continue with diagonalization in chapter 6.